So we can find the plus c if we can fix the antiderivative in some spot, in a position. So if I can antidifferentiate x squared into x cubed over 3 plus c, if I can say that this big F function passes through this coordinate right there, then I know it's got to be this line with the green slope and not this one, because only this graph passes through this one particular point. So fixing that position tells us which one of those lines we're dealing with. And it allows us to actually calculate plus c as well. So let's take a look at this. So we're going to actually calculate plus c, and we're going to be able to do this on the indefinite integral if we know the fixed position of x and y of the original function. So if I antidifferentiate this, I'm going to get 2x squared over 2 plus 3x plus c, and there's my antiderivative function I'm going to call y. Just simplifying that, that becomes x squared plus 3x plus c. Well, if I know that this graph can just go move up and down, but if I know the positioning of x and y, then I can actually plug in y is 5, x is 0, and that leaves me with a plus c as the only variable in this expression. And so I can get my plus c as c equals 5, which is my y-intercept. So y is equal to x squared plus 3x plus 5. There's my quadratic equation that has a derivative like this. Although there's many quadratic equations that have derivatives like this, the one that passes through this point we've calculated must be plus 5. So if I can fix a point on the antiderivative graph, that means I should be able to find plus c. So this is another situation. I've been given the derivative. I want to find the antiderivative. I know a point on the antiderivative. I know the x and y on that antiderivative function. So if I antidifferentiate this, okay, if I'm going to antidifferentiate this to negative x cubed over 3 plus 2x plus c, there's my antiderivative function. If I plug in my x and y, there's only one variable left to solve for. So solving for plus c, I get 6 equals negative 9 plus 6 plus c. C is equal to 9. Okay, so then my antiderivative equation ends up being, I can actually resolve that plus c because I know a position on that antiderivative function graph, and I'm going to write it as that y is my antiderivative of what was in the integral. Okay, so here's another last one here. If we have differential equation, okay, the differential equation, I've got dy by dx is equal to 2x plus 1. I'm going to find this original function. Again, I'm going to start relating this to the area function. Although we can just find the antiderivative of this, I'm just going to do something here. And I think I've done this before in some previous notes. I'm just going to move that over here. And when I move that piece over there, I have the change in y is equal to the height on the derivative function times the width. Remember that this is my area function. Height times width gives me the change in the original antiderivative function. If I sum up all those changes on both sides, there's my integral. Okay? So the sum of all the dy's is y's. Essentially, it's not quite true, but it's essentially true. And this is just the sum of all the areas. So the antiderivative works out to be 2e to the x plus c. Okay, and then I can solve for the plus c if I recognize that there is a point on the antiderivative function, y equals 3, when e equals 0. Okay, so c is equal to 1. So my final equation then is my antiderivative function big F, okay, which we call y, in this case is 2e to the x plus x and plus c, which we calculated to be 1. So there it is. There's my antiderivative function.